In this video we're going to look at our first two Laplace transform pairs. So we're going to look at the Laplace transform of a constant and also the Laplace transform of a function e to the at. So to start off with, the Laplace transform L f of t is equal to the integral from 0 to infinity of e to the minus st times the function f of t by dt, and that's all going to be equal to a function in the complex frequency domain f of s. So let's look at two examples here. If I was looking at the Laplace transform of a function e to the 4t, that's going to equal the integral from 0 to infinity of something times e to the minus st. So what is that something? Well, the something is simply the function here, e to the 4t. If I was looking at the Laplace transform of cos of t, it'd equal integral from 0 to infinity of something times e to the minus st by dt. So what is that something? Well, it's going to be the cos t. Now we're going to look at the Laplace transform of a constant. So the function f of t is just going to be a constant a. So for example, if we had a little graph here and we had a t-axis here, then it would just be a constant term. Okay, for example 1 or say minus 2. So the Laplace transform of function a is just going to equal the integral from 0 to infinity of our function, which is a, times e to the minus st by dt. Now we're integrating with respect to t, and a is not a function of t, it's just a constant. So we can take the a out of the integral sign and you'll have the integral from 0 to infinity of e to the minus st by dt. So we've seen something similar to that in the introductory video, so maybe you can go ahead and try it yourself and see whether you can get that answer. So here's the answer here. When we integrate e to the minus st, we get e to the minus st upon minus s, all times the constant a, and we're integrating that from 0 to infinity. We'll take the minus s out, we get minus a upon s e to the minus st from 0 to infinity. Now the only value here that we place the 0 and the infinity in is in t, because we're integrating with respect to t. So we can write minus a upon s, and as t tends to infinity, e to the minus st tends towards 0. Again, we've seen that in the introductory video. So we'd have a function that would look like this here. That's t, and this is e to the minus st. As t tends to infinity, e to the minus st just tends towards 0. And as t tends towards 0, e to the minus st tends towards e to the 0, n to the power of 0 is just equal to 1. So we get minus a upon s times 0 minus the 1. The minus and minus make a plus, so we get a upon s. So the final answer is the Laplace transform of a constant a is equal to a upon s. So let's try some examples. The Laplace transform of 5 is going to equal, well, it's going to be the constant 5 upon s. The Laplace transform of 1 is the constant 1 upon s. The Laplace transform of 172 is the constant 172 upon s. Now we'll look at our second Laplace transform, which is the Laplace transform of e to the at. So the Laplace transform of e to the at equals the integral from 0 to infinity of e to the minus st times e to the at by dt, and that equals, well, you can go and try that for yourself. I'll give you a little hint. We can take out a common factor here of minus t, and you'll have e to the minus s minus a times t. And you can use the same form of integration as you used in the last example, integration in the last example, in order to work that out. So here's the solution. Laplace transform of e to the at is equal to the integral from 0 to infinity of e to the minus st times e to the at by dt, which equals the integral from 0 to infinity. Now we'll take the common factor of minus t out, and we'll be left with s minus a. So whenever we integrate that, we've seen in the previous example, all that happens is the exponent here comes down underneath. So you'll be left with e to the minus s minus at upon minus s minus a from 0 to infinity. Now we can take the 1 upon minus 1 upon s minus a out, because we're integrating this here with respect to t. Okay, so s and a are not functions of that value of t. So we've got minus 1 upon s minus a, e to the minus s minus a times t, all from 0 to infinity. And again, as this term here, as t tends to infinity, this e to the minus s minus a times t is going to tend towards 0, and e to the 0 is going to equal a value of 1. So again, we're just going to get the 0 minus 1. So with the minus, we'll cancel with the minus, and we'll get 1 upon s minus a. So the Laplace transform of e to the at is equal to 1 upon s minus a. Let's look at two examples. The Laplace transform of e to the 5t is going to equal, well, it's going to be 1 upon s, and the value for a is 5, so it's s minus 5. The Laplace transform of e to the minus 2t will be 1 upon s. A is equal to minus 2, so the minus of minus 2 will make plus 2. So we have here a summary table of the Laplace transforms we've looked at so far, and we'll build up this summary table into a larger number of transform pairs as we work our way through the rest of the course. So t is the time domain, s is a complex frequency domain, a function of time, and the complex frequency domain will be a function of the complex frequency f of s. The Laplace transform of a constant a will be a upon s. The Laplace transform of a function e to the at will be 1 upon s minus a. So that's all there is for this video, and I'll get you on the next video where we'll look at a few more Laplace transforms. Goodbye.